Hello everybody, my name is Luke Metz, and I'm going to talking to you today about some work we've been doing on parallel training of deep networks with local updates. This has been joint work with Laskin. There's a number of ways to parallelize training of deep learning models. The first and most common technique is to leverage data parallel training. The idea here is to take a batch of data and split it up across machines, and then average the gradients across each machine. Another common approach is to leverage model parallelism. The idea here is to split up computation in each layer across each different machine. Finally, an up-and-coming technique, pipeline training. Here, we take each layer and put it on a different device, and then send data through from device 1 to device 2, device 3, and so on. There's a number of limitations of the existing methods, however. The first is diminishing returns with increasing batch size. In the figure to the right, I'm showing a number of steps required to reach a certain loss value as a function of batch size. In an ideal world, we would be on this dashed line. But in practice, however, as we grow batch size, we get worse and worse scaling performance, as denoted by this shift up on this blue curve. The second limitation is networking and communication costs. As we grow the number of nodes in our cluster, communication costs can grow substantially, and possibly up to n squared. Finally, some methods can lead to underutilization of hardware. And because this hardware is often special purpose and expensive, such as GPUs, this is quite undesirable. What we explore is a family of parallelization strategies we call local parallelism. The idea here is to split up computation so each layer can be trained in parallel. To show how this works, consider training this 4-layer network. With backprop, we would send a batch of data through the network, then backpropagate the gradient all the way back. With local methods, however, we first add auxiliary loss calculations after each layer. In our case, we use the same form as the output loss. So if we're using cross-entropy loss to some target class, we use the same thing for each layer. Next, to train this, we only compute gradients for each layer using only these auxiliary losses. And we don't ever propagate any information back through the entire network. You can see this by only showing the arrows pointing to the right between each layer. Once our network is divided in this way, we are free to spread each layer onto different machines to train. The only dependence between machines now is this forward passing of activations. From a systems perspective, local updates solve a number of existing problems with scaling. With regard to diminishing returns from batch size, local updates give another axis of parallelization. Namely, each layer, the layers themselves, can be trained in parallel. With regard to communication costs, the only information required is to send forward activations along the network. So it's much lower than, say, data parallel or model parallelism. And with regard to device utilization, each model can operate near non-stop, as we don't need to wait for any information other than forward passes from the previous layer. There's no network-wide synchronization, for example, like you would need with pipeline training. These improvements, however, come at a pretty big cost. When training in this way, the updates computed are biased. In some settings, this greedy approximation can lead to worse performance. So there are trade-offs. Before going further, I wanted to call out that this family of algorithm is not invented by us. Layer-wise pre-training has a really rich history, with some notable work by Bengio as early as 2007. Modern variants of the same type of algorithm have more recently been explored to train large CNNs as well as representation learning algorithms. I threw some links to a number of papers here if anyone's interested in learning more. In this work, our main focus is on scaling. To this end, we explore a large-scale study of multiple different kinds of local update methods with a focus on understanding how these methods scale with increasing compute. We also demonstrate how these methods can result in increased throughput when implemented on real hardware. There are a few kinds of local methods we explore. First, as a baseline, we explore backprop. Next, we explore the most greedy local update method, where each layer is trained entirely independently on separate machines. Next, we explore what we call overlapping. In this setting, layers are shared across groups of machines. So in this figure, we would have 3 machines running in parallel, but each layer shares a neighboring chunk. So this blue chunk is shared and this green chunk is shared. Finally, we explore chunked training. And this is similar to greedy training, but instead of backpropping each layer independently, we group layers and backprop into each of these groups. This lowers the amount of parallelization possible, but can often lead to less greedy gradient estimates and thus higher performance. The main tool we look at to understanding trade-offs between these methods are cost versus time training curves, inspired by an empirical model of large batch training. The idea here is we are free to choose what batch size and thus what hardware we can train on. In an ideal world, using more hardware for a shorter time would lead to identical costs. This corresponds to horizontal lines on this figure. In practice, however, we hit scaling issues, as we talked about earlier. This causes this slope to curve up as we increase the amount of hardware and batch sizes used. To generate these figures, we need to run a fair amount of experiments. So for a given algorithm, we try different batch sizes as well as different optimization hyperparameters, and then plot only the points on the Pareto frontier. First, we show this on training simple 8-layer CFAR10 MLPs. We show a sequence of these plots corresponding to different cutoff values, so to different loss values we're trying to achieve. On the x-axis, we have a hardware-independent measurement that represents wall clock time. This is basically the number of serial flops required to train in parallel. On the y-axis, we have a hardware-independent measurement of cost. In this case, total flops required. In each pane, we show a different cutoff value. In all these figures, we want a method to be in the bottom left. So this corresponds to low costs and training in a short amount of time. Now, depending on the cutoff value, these local methods can train dramatically faster if we're willing to pay a slight increase in cost. For example, in this 0.01 cutoff, the overlapping method can theoretically train models around 10x faster than backprop, with only a modest cost increase. Finally, there's no situation on any of these plots where backprop is actually part of the Pareto frontier, suggesting that no matter where you want to be on this trade-off, using one of these local methods is desirable. Next, we look to more realistic models, a transformer trained on the LM1B dataset. Once again, depending on the cutoff value, we see large improvement in training speed in the high-cost regime. So for example, here, we see quite a large improvement in wall clock time that's possible. But unlike the MLPs, however, when one does care about minimizing costs at the price of longer training times, backprop remains the most efficient algorithm. Finally, we have results on training ImageNet with ResNet 50. For this model, local updates work well when trying to achieve low accuracy values, say 50% or 60%. But when training to higher performance, we see local updates severely underperform backprop. In this highlighted pane, many of the local methods are not even on this plot, meaning that no method achieves the desired cutoff value. With this demonstration of performance gains from the previous section, we shift our attention to showing throughput on real hardware as compared to pipeline backprop. In each row, we show a different model family trained with different sized batches. In all settings, we find significant speedups over backprop. In some cases, up to 40% faster, as in the ResNet 101 case. To understand how this is possible, we visualize the execution traces for pipeline backprop using 4 chips. The red area denotes computation, and the gray boxes denote idle processors, or no computation being done. To understand what's going on here, let's first visualize a single microbatch of data flowing through this pipeline. First, we get data and run a forward pass on chip 1. This data then gets passed to each subsequent chip to perform a forward pass. And next, we perform backward passes, first on chip 4, chip 3, chip 2, chip 1. This is a single batch, however. For increased utilization, when doing pipeline training, we often run on more than one microbatch. So we can see another batch visualized here in green. As a result of this structure, there are different phases in backprop pipelining. There's this ramping up phase, where data is coming into the pipeline, a ramping down phase, where the last gradients are being calculated, and a steady state phase, where performance is at its peak. In this case, each chip or each layer is computing a forward and backward pass. It's these different stages, in particular ramping up and ramping down, which result in poor device utilization. In local updates, however, there's no need to send data back and down, and there's no need for global synchronization. So as a result, once an initial ramp up is done, the pipeline can run at steady state for all of training. and thus result in much higher utilization. In summary, we have shown that local updates can be used to leverage more compute and thus train models faster. This comes at the cost of approximate training methods, so they might lead to subpar performance depending on the problem. Finally, we showed that they can make effective use of hardware and result in high device utilization. When working on this project, we really wanted to push the limits on the amount of parallelization that can be done to train networks. We hope that this will enable both larger models and training of models faster in the future. Thank you all for listening. I'm not sure I'll have the ability to answer questions here, but please do reach out to any of us over email and we'll be happy to discuss more or answer questions. Thanks again.